So in this screencast, we're going to talk about phase diagrams and how they're sort of useful tools for talking about what state things are in. They're not really all that complicated once you sort of understand what their base definitions are. So we know that the physical state of a species is dependent on temperature and pressure. We've talked about how at normal pressures, water is a liquid at, say, 90 degrees, or 93 degrees Celsius. But if I go to Wyoming, because of the vapor pressure in Wyoming, that water can boil at 93 degrees. So if I have water, stable water at 95 degrees in Wyoming, it's a gas, simply because of its temperature and the ambient pressure. So by extension, we can do that for all pressures and all temperatures of a particular substance. And that's when we get something called a phase diagram. So we have generally these are written as temperature on the x-axis and pressure on the y-axis, and they all have sort of like the same generic shape in terms that there are three distinct regions of the phase diagram. And of course you need to know which one is which. So we'll talk about the generic shape first. So the easiest way to remember which zone is which, so one's a solid, one's a liquid, one's a gas, is just like remember what you know about solids, liquids, and gases. So way down here at low temperatures, at reasonable pressures, we know that things when they're very, very cold are always solid, especially if there's a lot of pressure. We know that if we go to very high temperatures, that no matter what the pressure is, it's going to be a gas. There's our solid, there's our gas. So obviously what is sort of in the middle is our liquid. So we also know that at a certain point, once we get to a very high temperature and a very high pressure, we hit what's known as the critical point. So that's sort of like the end of this particular liquid or gas. And generally the solid liquid line goes off into reasonably to infinity. It does not have its own critical point, so there's no critical point between sort of like solid liquid. Critical point is only between liquid and gas, so it's like the end of this long one. And we know that sort of above that pressure and that temperature, so everything in this sort of zone up here is again that supercritical fluid where it's not a gas, it's not a liquid, it's sort of, it looks kind of like a fog and is all that weirdness. This intersection is known as the triple point. And again, it's just sort of like it's a reference point because it's the one case. So here, if we're below this particular pressure, we know that the solution or the substance will actually go straight from a solid to a gas. So imagine if I'm down here and I'm keeping the pressure constant and I'm just slowly heating the substance, eventually I'll reach this line, which is the point where it goes from a solid to a gas. Now remember that's sublimation. Going from here to here, that is solid going to a liquid, that's melting, and going from liquid to a gas is vaporization. So if we think about, here is the temperature at which this particular substance goes from a liquid to a gas. So this temperature is sort of like the boiling point of this particular liquid at this pressure. And we can have, if we increase the pressure above it, we know that the boiling point will go up. Talked about that in the previous screencast, that the boiling point, remember what boiling is, it's going from liquid to gas. If we increase the ambient pressure, that temperature goes up. So obviously if we increase the pressure, the temperature goes up, and our graph sort of like confirms that. So here are two phase diagrams of, and as you can see, they have the same general shape. And one is on the left is water, and on the right is carbon dioxide. So here at 1 atmosphere pressure, atmosphere pressure is very close to 1 bar pressure, just a little bit different. So this is at 760 torr. So we see here at 1 atmosphere pressure the normal melting point. So we're going across, we start very, very cold, and then we get to 0 degrees Celsius. We hit that solid liquid barrier. So everything, this whole line can be thought of as the melting point, right? Because I could be melting down here, I can be melted up here, but every time I hit this line, that's when I'm melting. And remember, when I'm melting something, when I'm along that line, I have both the liquid and the solid phase together at the same time. Then as I go along and I'm heating up the water, and eventually again at 1 atmosphere, I eventually hit 100 degrees Celsius, the normal boiling point for water. So these are sort of like the two normal phase changes that we associate with taking, solid water below 0 degrees Celsius. And once we get to boiling, that it hits 0, blah, 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 blah. But again, this is emphasis that this temperature and this temperature are only because we are at this particular pressure. If we change this pressure, then those temperatures will obviously change. And it should be noted that there is a point down here below the triple point that we can make water actually sublime and go straight from solid to the vapor, which is just another way of saying gas. I took this picture from a British website. That's why it says vapeur. So we can actually make water sublime and actually not melt and actually have it go straight from solid to gas. Now, going from solid to gas is something that actually happens to carbon dioxide under normal circumstances. That's why we call it dry ice, because it doesn't go through the liquid phase. So at 1 atmosphere pressure on this graph, that falls down here. And as we take solid carbon dioxide and we slowly heat it up, it begins to sublime. The sublimation temperature at 1 atmosphere pressure is about minus 80 degrees Celsius. So at minus 80 degrees Celsius is when dry ice starts subliming. It goes straight from solid to vapor. Now, because of where we are, if you will, in our phase diagram, 1 atmosphere is sort of below this triple point. So we can actually make liquid carbon dioxide, which is actually kind of difficult because you've got to have a pressure greater than, I think it's 5 atmospheres or 5 bar. So you have to have a pretty sturdy container to maximize that, or to make it such that we're talking about a line up here, so we can actually go from solid to liquid to gas. So whether or not something sublimes at a particular pressure is basically a question of where is the triple point. So carbon dioxide sublimes at 1 atmosphere pressure because the triple point is above 1 atmosphere. And in the case of water, the triple point is below 1 atmosphere. So that's why it melts, turns into a liquid, and then actually has a liquid phase at that particular pressure. So there you go. Good luck.